So this video is about Beer's law, and what Beer's law does is it tells us how the absorbance of light corresponds to the concentration of a molecule in solution. And before we get to the statement of the law itself, I want to go over what's called UV vis spectroscopy. So this is the technique that we're going to be using in lab, and at its basis, what it does is you run different colors or different wavelengths of light through a sample, and you see how much of that light gets absorbed in the sample. So this shows a very basic schematic of it. We have a source. Okay, so there's a light source, and we'll pass some of that light through a slit. And then that light gets put through a prism or gets through a diffraction grating that can move kind of back and forth here. And as it moves back and forth, it's going to create a rainbow. It's going to move this light across a slit. And so in doing that, we can select different colors, different wavelengths of light. So that wavelength will pass through what's called a cuvette, and we have a detector on the other side. So what the detector can do is it can measure the intensity of light, okay, that has passed through the sample, and then it can convert that into what's called an absorbance or a transmittance. So a little bit of the theoretical underpinning of this. So we have the nucleus, and in the shell model, we have n equals 1, then we have n equals 2. Okay, and in order for, say we had an electron here, in order for that electron to go up to the n equals 2 level, there's a difference in energy between these two levels. So what it has to do is it has to absorb exactly that energy. And so this energy corresponds to frequency, remember our Planck equation. And so the result of this is that only certain frequencies of light correspond to these energy differences between shells, and therefore only those frequencies will be absorbed. Okay, so as light passes through, the electron takes that frequency out. It absorbs it and uses it in order to get excited up to a higher state. And you can imagine the more concentrated the molecule is in solution, the more of this light will be absorbed. So that's what Beer's law addresses, is this absorption of light. So what we can say, Beer's law, is we have this absorbance at some wavelength, lambda, and that's going to be equal to the path length. So that's going to be in centimeters. And what the path length corresponds to is this distance right here. Okay, how much of that cuvette, distance-wise, does the light have to pass through? So that's what the path length is, times the concentration. So this will be the concentration in molarity. Okay, so concentration in molarity. And then finally, we have this thing. This is called the molar extinction coefficient. And what the molar extinction coefficient does is it reflects how well the light of wavelength lambda gets absorbed by the sample. So absorbance has no units. So the molar extinction coefficient will have reciprocal molarity, reciprocal centimeters. Okay, units of that. And the higher the molar extinction coefficient is, the better the light of that wavelength gets absorbed. Another way to define absorbance, and this is kind of an FYI thing, so absorbance, if we take negative log base 10 of something called the transmittance, okay, so you can measure essentially the percent of light that was transmitted through the sample. You can also calculate absorbance that way. Transmittance. I mention this because very often when you use a UV vis spectrometer, you can get more accurate readings if you just record the transmittance and then convert back to the absorbance. Okay. So anyway, but this expression is what we're going to fill out. This is Beer's law. Okay. Absorbance is equal to path length times concentration times the extinction coefficient. So we can get the path length of our cuvette, and we can measure the absorbance using a spec. But if we want to find this concentration, we have to know what the molar extinction coefficient is for the compound that we're looking at. And that is obtained experimentally. And I wanted to show you a graph of how that's done. So this is a graph, and what you do is you plot you make these are called standard solutions. So you make a series of solutions of known concentration. These concentrations that you make up yourself and that you know. And then you measure the absorbance of each of these concentrations at a wavelength. So you notice here for this substance, they had a wavelength of 526 nanometers, with some uncertainty because of what's called the bandwidth of the spectrometer. So they said, okay, we choose this wavelength, and we're going to measure the absorbance of some known concentrations. They used micromolar at a series of wavelengths, and you get this graph. And this graph, again, we have Beer's law. Absorbance is equal to L epsilon concentration. Well, we know what concentration is. We know what absorbance is. And if you have a path length of 1 centimeter, and very often you do, then the slope, okay, the slope of this will be your molar extinction coefficient if L is equal to 1 centimeter. Okay, so what we're going to be doing in lab is you guys are going to make up a series of solutions, and you're going to have concentrations. You're going to make up a bunch of known concentrate solutions, okay? And then you're going to measure the absorbance at these different concentrations, and you're going to get dots, and you're going to fit that, and based on the slope, you're going to get the molar extinction coefficient. Okay, so that's what you're going to be up to at the next lab period. So let me know if you guys have any questions.